now, Tara.
Are you though?
You're gonna beat him.
Oh no, you're going down.
Andrew? What are you guys doing in my house? Why are you guys playing Brawl?
Brawl is awesome.
But Mario Kart's better. Alright, let's play Mario Kart then.
Okay.
Yeah.
Mario time! Oh yeah, Luigi!
Yes, Peach! Yes, Daisy!
Mario and Luigi are approaching each other as the path of the racetrack intersects. If their intersection point were the origin of a coordinate plane, Luigi is 6 miles to the west of the intersection point, moving east at 75 miles per hour, and Mario is 5 miles north of the intersection point, moving south at 70 miles per hour. How fast is the distance between Mario and Luigi decreasing? In order to solve this problem, we can think of Mario and Luigi's positions as lying on a coordinate grid. This allows us to formulate a relationship of related rates in order to solve this problem. First, let's label everything that we know. Notice that Mario's speed is negative because he approaches the intersection point heading south, and Luigi's speed is positive because he approaches the intersection going east. Great! Now that we have what we know, let's see what relationships we can come up with in order to solve the problem. First, we should notice that we have a right triangle, which gives us a tremendous Pythagorean relationship to use. Now we can use our Pythagorean relationship to find the initial distance between Mario and Luigi. Notice that the Pythagorean theorem is also another form of the distance formula. Plug Luigi's coordinate position of -6 in for A, Mario's coordinate position of 5 for B, and find C. After finding C, you may ask, what could we possibly do next? Well, luckily, we can find the derivative of the Pythagorean theorem with respect to time in order to find the rate of change of Mario's motion, Luigi's motion, and the distance between them. First, do the initial derision with variables. Next, plug in what we know. Take note that we have been given Mario and Luigi's speed, which can also be called rates of change. Plug in the numbers for the A, B, and C variables and the rates of change that correspond to Luigi and Mario's variables, and solve for the rate of change of the C variable, which is the rate of change of the distance between Mario and Luigi. After plugging in all our numbers and simplifying everything, we find that the rate of change of the distance between Mario and Luigi is 102.43 miles per hour. Keep in mind that this rate of change is negative because distance between them is decreasing. So, the distance between Mario and Luigi is decreasing at a rate of 102.43 miles per hour.
While racing, Daisy encounters some slippery obstacles. To avoid them, some special maneuvers had to be made. While reviewing the footage, there is something interesting. If you take the footage and flip it on its side, it almost looks like a function. By tracing the car's motion, it is possible to get a graph of the car's position. After finding an auto-fit for the graph, it can be further analyzed to reveal the critical values, extrema, points of inflection, and intervals where the function is increasing, decreasing, concave up, or concave down. The first step in finding this information is to take the derivative of the function. To prepare for later steps, it's also a good idea to find the second derivative. After this, solve the derivative for 0. Using synthetic division, the first 0 can be found. After this, the quadratic equation was applied to find the remaining two. These values for which f prime of x equals 0 are the critical values of the function. By using a sign chart, it is possible to determine whether the critical values are maxima, minima, or neither. Plugging values into the derivative function and determining if they are positive or negative, then analyzing for sign changes verifies that there are two minimums and one maximum. By plugging these values of x back into the original equation, the y values are given, which produces an ordered pair for each maximum and minimum. Using all of this information, it is possible to determine when the function is increasing and decreasing. Going back to the second derivative of the function, which was found earlier, it can be used to find the inflection points in the function. Using the quadratic equation to solve the second derivative for 0 reveals the x values of these points. By plugging these x values into the original equation, the y values can be found, creating two ordered pairs for the points of inflection found in the function. By creating another sign chart with the second derivative, the points of inflection are verified. The sign chart also reveals when the function is concave up and concave down, which further verifies the maxima and minima found earlier. In the end, two minima, one maximum, 2 points of inflection, and areas where the function is increasing, decreasing, concave up, and concave down have all been found.
Princess Peach and Daisy are traveling on perpendicular lines to a point where they will meet. Daisy is currently 0.8 miles from the meeting point and approaching at 60 miles per hour. Princess Peach is 0.6 miles away and approaching at a speed of 30 miles per hour. How fast is the distance between them changing? Is it increasing or decreasing? Let the distance between Daisy and the meeting point, or 0.8 miles, equal y. We know that y equals 0.8 miles. We also know that the rate at which y is changing is a decrease by 60 miles per hour, because although Daisy moves at 60 miles every hour, the distance between her and the meeting point decreases by 60 miles every hour, so it is negative. So dy dt equals negative 60 miles per hour. Similarly, let 0.6 miles equal x, and Princess Peach's distance is decreasing by 30 miles every hour, so dx dt equals negative 30 miles an hour. Now let's create a relationship between x, y, and s that we can differentiate with respect to time. Let's use the Pythagorean theorem. X squared plus y squared equals s squared. We can then take the derivative of both sides with respect to time to get a relationship. When you derive everything, you will notice that it uses the chain rule. Now let's use the Pythagorean theorem to solve for s. X squared plus y squared equals s squared, so 0.6 squared plus 0.8 squared equals s squared. This gives us s squared equals 1, so s equals 1. Now let's plug in what we know and try to solve for ds dt. Once we plug everything in, we can see that negative 132 equals 2 times ds dt. Therefore, ds dt equals negative 66 miles an hour. This is the rate at which the distance is changing with respect to time. Since we got a negative number, we can see that as time goes, the distance between Peach and Daisy is decreasing. This makes sense, because as time goes on, they are getting closer to the meeting point, so they are getting closer to each other.
After Mario beat Luigi by a good 15 seconds in the race, Mario decided to showcase his victory with a classy and respectful donut around Luigi's car. Now, Mario entered the donut at 8 miles an hour and continued around Luigi for 2 revolutions, all while being able to keep this constant speed. It took 8 seconds for Mario to complete a single revolution around Luigi's car, and he did it at a constant 15 feet away from the car at all times. What Mario really wants to know is if he can come up with an equation for the rate of change of the angle with respect of time in seconds from the starting point of the car to the end of the first revolution. He also wants to restart the degree count past the first revolution and into the second revolution, requiring a second equation. Let's look at the problem a little more in depth. So the problem Mario has created in this situation involves a car traveling in a circle around a center point, which happens to be Luigi. and taking into account the distance of 15 feet from the center of Luigi's car, this can be used as the radius of the circle because Mario travels around Luigi at a constant distance. What is the actual distance that Mario has to travel for him to complete a single revolution? To find the length of the perimeter of a circle, you must use the circumference formula, which is 2 pi r, and you should know that by now. And plugging in the known variable of r equals 15 feet, the circumference is equal to 30 pi. With this number known, we now need to find the amount of time it takes for Mario to travel this distance with respect to his speed. The equation v equals d divided by t represents this situation, with v being the speed of the car, d being the distance, and t being the time taken to travel that distance. When reworking the formula, solve for t and we find that t equals v over d. Plug in the known variables and get t equals 30 pi feet divided by 8 miles an hour. We now must change the bases of the variables yada yada yada, bam bam bam, and we are there. It shows that it takes about 8 seconds for Mario to complete a single lap around Luigi. Knowing this, we can look at the circle in radians, being 2 pi for one complete circle and 4 pi for 2 complete circles, and dividing that by our found 8 seconds gives us the angle change over 1 second is pi divided by 4, or 45 degrees. That's good stuff. We can make the equation for Mario to find what angle he is located at in any period during his donut session. In order to create the first equation, we only need to take pi over 4, or 45 degrees, and multiply it by the desired time. This is because the degree stays between 0 and 2 pi, or 360 degrees. The equations are f of t equals pi over 4 times t, or f of t equals 45 degrees times t. For the second equation, we only need to subtract the first revolution's degree count, because as soon as you pass the first revolution, the time does not return to 0. For example, if we want the angle at time 10 seconds, the former equation would give us 10 pi over 4, or 450 degrees. Therefore, if we take away 2 pi, or 360 degrees from those equations, they could also work for the second revolution, making the new equations of g of t equals, in parentheses, pi over 4 times t minus 2 pi, or g of t equals 45 degrees times t minus 360. Mario can now find his angle and continue his winning streak. Congrats, Mario!
This is kind of boring now. I hate Mario Kart.
I don't like it. That's whatever.
No fun.
Bye, AJ.
Alright, see you, AJ. You suck.